Hello physicists. Today we're going to have a look at the SQA's National 5 physics paper from 2017 and focus on the multiple choice questions from section 1. So, question number 1. A cyclist is travelling along a straight road. The graph shows how the velocity of the cyclist varies with time. The kinetic energy of the cyclist is greatest at... So, we should know that kinetic energy is equal to 1/2 mv squared. Therefore, the greater the speed that the cyclist is moving, the greater the kinetic energy. The point on the graph with the greatest speed is point P, which is answer A. Question 2. A circuit is set up as shown. The reading on ammeter A1 is 5 amps. The reading on ammeter A2 is 2 amps. The charge passing through the lamp in 30 seconds is... Okay, so the first thing that we need to realise here is that 5 amps is leaving that power supply there and coming around the circuit. But when it comes to the parallel section in the circuit, that current splits. 2 amps going along the middle branch through the resistor and 5 minus 2, which leaves 3 amps, to pass through the lamp. Now we can use the formula Q equals I times T, current times time, so 3 amps times 30 seconds, which gives us 90 coulombs. Answer B. Number 3. A lamp is connected to a constant voltage power supply. The power supply is switched on. The graph shows how the current in the lamp varies with time. Which row in the table shows what happens to the current and resistance of the lamp between 0.05 seconds and 0.45 seconds? Well, if we have a look at that there, we can see that the current is definitely decreasing. If the current is decreasing, then the resistance must have increased at the same time. Answer A. Question 4. A circuit is set up as shown. The purpose of the transistor is the purpose of any transistor is to be an electronic switch. And in this case, it's an electronic switch, which is going to switch on the motor. Number 5. 5 students each carry out an experiment to determine the specific heat capacity of copper. The setup used by each student is shown. The student with the setup that would allow the most accurate value for the specific heat capacity of copper is determined to be, well, what have we got going on here? We have 5 different setups. Some of the setups have insulation wrapped around the copper block. Insulation will stop heat being lost to the surroundings and will stop the heater from heating the air around about the block, which means there would be a more efficient transfer of heat into the block. So that would improve it. So student 2 and student 5 have that. Additionally, if we're measuring the specific heat capacity of copper and to find out how transferring energy to copper causes its temperature to increase, we need to be measuring the temperature of the copper. You'll notice student 2 has inserted his thermometer into the copper block, where student 5 has left the thermometer outside. The thermometer in the block will give us a more accurate reading of the temperature of the copper block. So student number 2 has got the better setup. So that gives us answer B. Number 6. The mass of a spacecraft is 1,200 kilograms. The spacecraft lands on the surface of a planet. The gravitational field strength on the surface of the planet is 5 newtons per kilogram. The spacecraft rests on 3 pads. The total area of the 3 pads is 1.5 square meters. The pressure exerted by these pads on the surface of the planet is... So, pressure is force over area. We need to know what force the spacecraft acts on the planet. The force that the spacecraft acts is going to be its weight. So, W equals M times G. Its mass, 1,200, times the gravitational field strength on the planet, which is 5, which gives us 6,000 newtons worth of force. The pressure, as we said, is force over area, which in this case is 6,000 newtons divided by a total area of the 3 pads of 1.5 square meters, which gives us a pressure of 4,000 pascals, or 4 times 10 to the power 3 pascals, which is answer D. Question number 7. A solid is heated from minus 15 degrees Celsius to 60 degrees Celsius. The temperature change in the solid is, well, all we need to do is do 60 minus 15, which gets us to 75. 15 degrees from minus 15 degrees to 0, and then another 60 degrees from 0 up to 60, which gives us a total of 75. The fact that these temperatures are measured in Celsius and we want an answer in Kelvin is not really relevant here, because a change in temperature in Kelvin is the same as a change in temperature in Celsius. We can prove this. If we'd changed the initial temperature of 15 Celsius in minus 15 Celsius into Kelvin rather, we get 258 Kelvin. If we change the final temperature of 60 Celsius into Kelvin, we get 333 Kelvin. The difference in temperature is still 75 Kelvin, so we didn't need to do the conversion. Answer B, 75 Kelvin. Number 8. A student makes the following statements about waves. In a transverse wave, the particles vibrate parallel to the direction of travel of the wave. Light waves and water waves are both transverse waves. Sound waves are longitudinal waves. Which of these statements is or are correct? Well, let's consider the first one first. In a transverse wave, the particles vibrate parallel to the direction of the wave. Well, here's a transverse wave. And in this one, we can see the particles are vibrating in the vertical plane, whereas the wave is moving left to right. So the particles are not vibrating parallel to the direction of the wave, they are vibrating perpendicular to the direction of the wave. So that is incorrect. The second statement, light waves and water waves are both transverse waves. Well, that is true. Sound waves are longitudinal waves. That is true. So both 2 and 3 are correct. So that gives us answer E. Number 9, the diagram represents a wave traveling from X to Y. The wave travels from X to Y in a time of 0.5 seconds. Which row in the table shows the amplitude, wavelength, and frequency of this wave? So first of all, we consider the amplitude. The amplitude is the displacement of the wave from its rest position vertically, up to the top or down to the bottom of its crest. So here we've got a total height of the wave of 2.6 meters, which gives us an amplitude from the central line up to the crest, or the central line down to the trough, of half of that, which is 1.3 meters. The wavelength, well, we can see the length there is measured as 12 meters. How many waves does that make up? Well, the wave starts here. 1 wave takes us to there. 2 waves, 3 waves, 4 waves. So 4 waves in 12 meters. The wavelength is 12 divided by 4, which is 3 meters. And finally, the frequency. Well, on our data sheet, we have a formula that says frequency equals n over t, the number of waves divided by time. The number of waves, as we've just said, is 4. The time, as the question says, is 0.5 seconds. So 4 divided by 0.5 gives us 8 hertz, which gives us an answer of amplitude 1.3, wavelength 3, and frequency 8, which is answer C. Number 10, a microwave signal is transmitted by a radar station. The signal is reflected from an aeroplane. The aeroplane is at a height of 30 kilometers directly above the radar station. The time between the signal being transmitted and reflected signal being received back at the radar station is... So, there's our radar station. There's our plane. Now, the radar signal has to travel 30 kilometers to get from the radar station to the plane. But then it reflects off the plane, so has to travel an additional 30 kilometers back again. So, if we want to work out the time that it takes, we can use distance equals speed times time. The distance is 60 kilometers, or twice 30 kilometers. The speed because these are microwaves, part of the electromagnetic spectrum, is 3 times 10 to the power of 8. So the time is going to be 60 kilometers, or 60 times 10 to the power of 3 meters, divided by 3 times 10 to the power of 8, which gives us 2 times 10 to the power of minus 4 seconds. Answer C. Number 11. A member of the electromagnetic spectrum has a shorter wavelength than visible light and a lower frequency than X-rays. This type of radiation is, well, we need to know the spectrum first of all. Gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, TV waves, radio waves. I remember good xylophones usually vibrate intensely, meanwhile tambourines rattle. But what does that tell us? Well, the gamma rays are at the short wavelength, high frequency end of the spectrum, and the radio waves are at the long wavelength, low frequency end of the spectrum. So we're looking for the wave that has a wavelength shorter than visible light. So we're looking for the wave that is to the left of visible on the scale there, and has a lower frequency than X-rays. So lower frequencies towards the right-hand side, so the one to the right of X-rays. And you'll see the wave to the right of X-rays and to the left of visible is ultraviolet, which is answer B. Number 12. The diagram shows the path of a ray of red light as it passes from air into a glass block. Which row in the table shows the angle of incidence and angle of refraction? Well, the angle of incidence is the incoming ray. So the angle of the incoming ray measured between the light ray and the normal, the dashed line there, is that one. The angle of refraction is the angle between the refracted ray and the normal, which is that one. So angle of incidence is Q, angle of refraction is S. So the answer is A. Number 13. A sample of tissue is exposed to 15 micrograys of alpha radiation and 20 micrograys of gamma radiation. The total equivalent dose received by the tissue is... So, we'll consider the alpha first. We want to find equivalent dose, which is H equals dWr, so absorbed dose multiplied by the radiation weighting factor. The radiation weighting factor for alpha is 20. The absorbed dose is 15 micrograys. So 15 times 20. I know that radiation weighting factor, by the way, because it's given in the data sheet at the front of the exam paper. So there you can see alpha is 20. And that gives us an equivalent dose of 300 microsieverts from alpha. We need to do the same with the gamma source, though. It's same formula. If we look on that table again, the radiation weighting factor for gamma is 1. So we just multiply the 20 micrograys by 1, which gets us 20 microsieverts. Therefore, the total equivalent dose is going to be 20 plus 30, which is 20 plus 300 rather, which is 320 microsieverts. Answer B. Number 14. Two forces act on an object as shown. The resultant force acting on the object is, well, if we look at these two forces, we can consider that the object will be forced down towards the bottom left of the screen in that sort of direction. And we can complete a right-angled triangle where the two shorter sides are 40 and 30, and the hypotenuse is the overall force that we're trying to find out. So if we have a right-angled triangle, we can work out the length of the hypotenuse using Pythagoras. So the force is going to be the square root of the sum of the squares of the other two sides, which is square root of 40 plus square root of 40 squared plus 30 squared, which is 50. So the size of the force is 50 newtons, but we already knew that because all the options are 50 newtons. The direction, though, well, we can work out that angle. We have the adjacent and opposite sides of that triangle there. Tan is opposite over adjacent. The opposite is 30, the adjacent 40. So tan of that angle is 30 over 40, or 3/4. So the angle X is going to be inverse tan of 3/4, which is 37 degrees. Now, that's not one of my options either. But that's not a bearing, that's why. The bearing has to come clockwise from north. So if we consider north up there, to go from north to south clockwise gets us 180 degrees. But then this is a further 37 degrees round from there. So 180 plus 37 gives us a bearing of 217. So the correct answer is C, 50 newtons at a bearing of 217. Number 15. The graph shows how the velocity v of an object varies with time. The graph could represent the motion of, well, what's happening here? Initially, we've got the velocity decreasing from some value towards zero. And it's a positive value, it's above zero. Then at that point there, the velocity is zero. So the object would instantaneously stop. And then you can see on the other side, the line on the graph goes from positive to negative. That indicates a change in direction. And here we have the line moving away from zero, so increasing, but in the negative direction. So something is slowing down in one direction until it stops and then speeds up in the other direction. So which of the options would satisfy that criteria? Well, a ball falling freely downwards would not change direction. It continues to fall in one direction, so it's not that. A rocket accelerating upwards accelerates in one direction, upwards. A ball thrown into the air, then falling back to Earth, well, if we imagine throwing a ball up into the air, it would slow down as it gets higher until it gets to the highest point of its trajectory, and then it would start to speed back up again on the way down. So answer C is correct. D, a ball falling to Earth from rest and then rebounding upwards again. Well, if it fell from rest, then the line would be sloping upwards as it increases its speed towards Earth. So it's not D. And a car slowing to a halt, then accelerating in the same direction, well, it doesn't have a change in direction. It would slow down and then speed up again, but the line would never cross that horizontal axis of the graph. The answer is C. Number 16. A trolley is released from rest at point X and moves with a constant acceleration on a slope as shown. The computer displays the acceleration and average velocity of the trolley between the light gates. The trolley is now released from point Y, which you can see is further down the slope. Which row in the table shows how the acceleration and average velocity compare with the previous results obtained? Well, if it's accelerating from Y rather than X, the slope itself doesn't change. So therefore, the force that's pulling the trolley down the slope is not going to change. And therefore, there will be no change in the acceleration of the trolley. However, because it has been accelerating for less time when it reaches the light gates, it will not have been going as fast by the time it gets to the light gates. And therefore, it will be moving with a lesser average velocity. So the answer is E. Number 17. A rocket accelerates vertically upwards from the surface of Earth. An identical rocket accelerates vertically upwards from the surface of Mars. The engine thrust from each rocket is the same. Which row in the table shows how the weight of the rocket and the unbalanced forces on the rocket compares on Mars and Earth? So, what is the difference between Mars and Earth? If we look on our data sheet, we have this table, which tells us the gravitational field strength on different planets. And we see Earth has a gravitational field strength of 9.8, whereas Mars has a gravitational field strength of 3.7 newtons per kilogram. And that tells us that the force of gravity acting on the rocket on Mars is a little bit less than half that on Earth. So let's consider. The weight is going to be less on Mars because the gravitational field strength is less. What about the unbalanced force? Well, if we think about Earth and Mars, and we've got this identical rocket with an identical thrust, on Earth, the weight is large. On Mars, the weight is less. A smaller weight means that the unbalanced force, so the difference between the thrust and the weight on Mars, is going to be greater than the difference between the thrust and the weight on Earth, because they have the same thrust, but the Earth's weight is larger than Mars's weight. Answer D. Number 18, a satellite is in a circular orbit around a planet. A group of students makes the following statements about the satellite. The greater the altitude of a satellite, the shorter its orbital period. The satellite has constant vertical acceleration, and as the satellite orbits the planet, its vertical velocity increases. Which of these statements is or are correct? Well, firstly, the greater the altitude of the satellite, the shorter its orbital period is not correct. The further out the satellite is, so the greater its altitude, the longer its orbital period would be. 2. The satellite has a constant vertical acceleration. That is true. The satellite is in free fall around about the Earth. It is being influenced by the Earth's gravitational force, is causing it to accelerate towards Earth at the gravitational acceleration at the height that it is at. As the satellite orbits the planet, its vertical velocity increases. That's not true. Although it has a vertical acceleration, that does not result in an increase in its vertical velocity. What happens is, remember, velocity is a vector. It has both magnitude and direction. An acceleration is a change in velocity over a period of time. That change in velocity does not necessarily have to be in the size of the velocity. It can be in the direction of the velocity. And that's what happens in the satellite. So although it is accelerating towards the Earth, that acceleration does not alter the magnitude of the satellite's velocity. It alters the direction of the satellite's velocity and therefore causes it to orbit the planet. So that is not correct. The only one that is correct is 2. So answer B. Number 19. A heater transfers energy to boiling water at a rate of 1,130 joules every second. The maximum mass of water converted to steam in 2 minutes is, well, we're changing the state of the water. So we're going to use our formula EH equals mL, where L is the latent heat of vaporization of water, which we can get on our data sheet. And we can see it is 22.6 times 10 to the power 5 joules per kilogram. So we can insert these numbers into our formula. And we get a mass of 5 times 10 to the power of minus 4 kilograms. That, however, is the mass that is being converted to steam each second, because it tells us that the energy that's being transferred to the water is 1,130 joules each second. So if that amount of mass is converted each second, and the question asks us how much mass is converted in 2 minutes, we need to multiply that by the number of seconds in 2 minutes, which is 120, which gives us a total mass of 0.06 kilograms, which is answer B. And the final question in this paper. Light from stars can be split into line spectra of different colours. The line spectra from 3 stars, X, Y, and Z, are shown, along with the line spectra of the elements helium and hydrogen. Hydrogen or helium are both present in which stars? Well, how are we going to know? We will know if the lines present in helium and hydrogen are all present in a star, then that element is present in the star. So let's consider helium first of all and look at the line spectra working from left to right. So looking at the leftmost line of helium, we see that that line is present in star X, Y, and Z. If we look at the next line in helium, we'll see that line is also present in star X, Y, and Z. Indeed, so is the next line, and the next line, and the next line. So helium is present in star X, star Y, and star Z. Now let's consider hydrogen. There are only 2 lines in hydrogen, so let's consider the first one first. So that line there is present in star X and star Y. Star X and star Z, but not in star Y. Because it's not in star Y, if one of these lines is not present in star Y, then that means hydrogen is not there. So star Y contains helium only. Let's consider the other line of hydrogen to see if it's present in star X or Z. So the other line of hydrogen we can see lines up with one of the lines in star X and one of the lines in star Z. So both star X and star Z also contain hydrogen. Star Z, you can see, has another set of lines as well. So star X contains only hydrogen and helium, because hydrogen and helium account for all the lines in star X. Star Z contains hydrogen and helium and some other element, which accounts for the other 3 lines not already accounted for. So the answer is star X and star Z, which is answer D. And that completes the 2017 National 5 Physics paper, section 1. I hope you found this helpful, and we will have a look at section 2 of the paper and the different topics within it some other time. Goodbye for now.